welcome you all to the post-lunch session. I'm really happy to announce today that we have with us Professor Devashish Kundu from IIT Kanpur. I know him for quite some time. He has done his BStat MStat from ISI, then PhD from Pennsylvania State University under the supervision of Professor C.R. Rao, the well-known figure. He is right now Rahul and Nandini Gautam Chair Professor of IIT Kanpur, Department of Mathematics and Statistics. I am really happy to tell you one thing, that he is in a department whose name is Mathematics and Statistics, and quite, I think it was a couple of years back, I went once to one conference there in Kanpur, although after that I have gone a number of times. But I am really happy to tell this thing. That time the then director told officially in the this inaugural session that the way statistics people are doing in the department, very shortly probably we have to change the name from mathematics and statistics to statistics and mathematics. This is the way statistics department is of the IIT Kanpur. One personal thing I am going to share here, which really has changed myself after some statement of Professor Devashish Kundu long back in one IIT question paper setting we met. There, Professor Kundu was in favor of giving one question for uniform distribution, and I told, probably you have forgot, I told that it is really very easy question, why you are setting that? Then his reply was, also for a long time you are just used to this particular problem, that's why you are thinking it is too easy, but it is really not easy as far as the new students are concerned. From that day onwards, now really I have learned one thing, I am also now following the same thing, that whenever I have to set some question, I have to think, when I was student, if this type of question was given, whether I would have been able to answer this question or not. This is really a, great lesson I have learned from Professor Kundu. He is a great teacher, no doubt about it, and no doubt very good researcher. He works in different fields: statistical signal processing, nonlinear regression, survival analysis, generalized exponential distribution, statistical computing, and so on. So I am very sure that from the talk of Professor Kundu, we will learn a lot and we will also enjoy. And one thing I can tell you, that after lunch, generally we have the tendency to sleep. With full confidence, I can tell you that in this talk, you will not be able to sleep, even if you try to do so. Professor Kundu, please.
Thank you, Ashok, for the kind and nice introduction. When I got this invitation, I was really charmed. And when everyone told me to choose two lectures on the same thing, on the signal processing, which is my passion for quite some time. But I had decided that, let me break it into two. One is my long time love or passion, whatever you say, on the signal processing one. And the second one I'll be talking about, which is I'm currently working on, which is on the bivariate distributions with singular components. So that is anyway, that is my second talk. So let me start with that, the first one, which is control F, control L. Yeah. So the reason, actually I'm working on this one for quite some time, starting from my PhD one, and one thing I would like to put this one. So this is one of the areas. It's very interesting in the sense, maybe 90% of the people, those who are not in proper statistics, they are mainly engineers, particularly the electrical engineers. But interestingly, if you look at maybe 90% of the problem are purely statistical in nature. Okay, so I sincerely feel that if you understand the problem, if you can formulate the problem, definitely we can do a better job. Okay, and well, this is the sentence which was not by me, which was by Professor Rao, and in fact, that's what it happened almost like 30 years back. After when I finished my comprehensive, and he was kindly agreed to be my advisor. The first day when I met him, he said this one, that look, he gave me actually 3 theses. 2 of them are in the electrical engineering, and 1 of them in the computational mathematics. And he said this one, that look, I think they are trying to solve the problem, but as a statisticians, I think we can do a better job. Okay, if you can solve the problem, I'll give you PhD. So that's the way. And I sincerely, I mean, I sincerely hope that that is actually a very, very correct statement. I mean, and the main idea of my talk today, which will be maybe around 1 hour 15 minutes or 1.5 hours, I'll be giving the several problems which can be tackled, I think, by the statisticians in a much better way. Okay, so we will be talking about the kind of things what we have done along the years for quite some time, and we'll see this one, that there are lots of interesting problems, I think, which we can do a better job, according to Professor Rao. Okay, so yeah, so again, I mean, when Ashok and everyone invited me, Ashok was telling me this one, that well, Devashish, why don't you talk about the chart models what we are working on, and that's what I thought. I mean, actually, we have quite a bit of materials on that, but I think we need a proper background to go into this one, and so that's the reason this one, that I'll go back a little bit before, start with one of the most basic model in signal processing. Okay, I'll start from there. I mean, one of the most basic model in signal processing, and that I call this one as the first model. That's what I'll be talking about. Let me see. Is this working? No, I don't think this works. No? One second. Oh, okay, fine. Great. Yeah. So that's the reason this one, that I'll call this one as the first model, which is I think one of the most fundamental model in the statistical signal processing literature, and then we'll be talking about how it has been formulated actually. Okay, so we'll go back a little bit and see this one, that the basic formulation of the model, how it came. And of course, I'll be talking about the different estimation procedures. And well, I mean, I'm kind of biased. Okay, so I'm not going to talk about. There is a huge literature in the engineering one. There are lots of these, the heuristic approach and all these things. I will not go through this one. Okay, so I'll be mainly concentrating on those things where we have a nice theoretical results. Okay, and I think there. That is the difference. I think we have to always keep it in mind, the difference between the statisticians and engineers in that sense. So I will be mainly talking about the different estimation procedures where we have a nice theoretical results, nice theoretical backing to come up with an estimator rather than having a completely heuristic one. Okay, and then I'll be coming to the second model, which that is my main one, which we are currently working on, which is the chart model. And again, we'll be introducing the model, which you'll see this one, that it is coming out as an extension of the first one. And again, when I'll be talking about the several estimation procedures, exactly the same methods I'm going to follow, that there are huge number of estimation procedures which are available. Okay, as I said, there are lots of these heuristic approaches which are available. It works, but we really do not know how it works and things like that. So we will be talking about that. And then I think this is the place where you will see this one, that the lots of these open problems which are coming out. Okay, so these are the things I will be just mentioning about that. Some of the related models which are being used extensively in the different areas. I'll be talking about that, and of course, collaborators and the references. And okay, so let's start with that. Okay, let's start with the first model. And what we are trying to do, basically, we are trying to model the periodic data. Okay, so that is basically our whole aim. Okay, that's what we are trying to do, and we observe this periodic phenomena every day in our lives. Okay, it doesn't really matter. I mean, if you look at the number of tourists which are visiting the famous Taj Mahal, or if you're looking at the daily temperature in Delhi, or if you're looking at this ECG data, EEG data, and things like that, we'll see this one that all of them are very, very periodic in nature. Okay, I'll call this one it's a periodic, or it's a nearly periodic. Okay, that's what it is. So you will see this one that that's what all these data indicate, and sometimes, as I said, may not be exactly periodic, but it's a nearly periodic one. And our final aim, that our aim is to analyze such periodic data, or the nearly periodic data. Okay, so this is basically our problem. So problem is kind of very, very well stated. I mean, we don't have to think too much about exactly what it is. Okay, so the two question comes. Okay, first of all, what do you mean by a periodic data? That's a natural thing. I mean, what it is? Okay, can you give a formal definitions, or if not, at least we can understand. Looking at the picture, looking at the graphs, do you follow this one? Do you understand this one? So that is the first question. What is a periodic data? That's what we are trying to get it. And of course, I think more fundamental question is, why do we care to analyze? I mean, well, it is there. I mean, you have a periodic data. I mean, why do you care to analyze? I mean, does it really give us something? Okay, so let's look at what is a periodic data. Well, I'm not going to give you a formal definition. There is no need, actually. Okay, so we do not need to give a formal definition of the periodic data, but informally, what we can say this one, that actually this periodic data can happen in 1 dimensions, 2 dimensions, even in 3 dimensions also. And that's what we'll be showing some of the pictures where you can see this one, that we have a periodic data in all dimensions. Okay, so first of all, if you look at the periodic data in 1 dimension, it basically shows it has a repeated pattern. Okay, it has a repeated pattern. Basically, it comes back again and again along the same way. That's what it is. Roughly speaking, I'll call this one as a periodic data. So it comes back. It comes back again and again, or it has a periodic pattern, or a repeated pattern. If you go to the higher dimension, from 1 dimension to 2 dimensions, if you go to that, it has a periodic pattern, and what it is, which is basically a symmetric in nature. Okay? Symmetric in nature in the 2 dimensions, and if you look at the 3 dimension also, you will see this one, that there is a symmetric nature. When you see the pictures, I think it will be absolutely clear. I mean, you don't have to. That's a reason that I do not want to give a formal definition. It's not needed, actually. Okay? So looking at the data itself, it should not be too difficult to come up to mentioning this one, that, well, it is a periodic data. Okay, the second question, why do you care to analyze? Why do you really want to analyze this one? Of course, the first one is purely for our own curiosity. I mean, we are trying to find out a theoretical reason, and we're trying to find out a theoretical model, and things like that. And which is there, which kind of passion we always have. I mean, trying to make it more analytical, trying to make it more statistical, more mathematical, and things like that. So definitely that is an important one, which is a theoretical reason that I'm trying to analyze a periodic data. But I think it has a lots of applications. Why do we need this one? And one thing is that for the prediction purposes, we'll see the example that where if it is a periodic data, and why the prediction comes into picture. I mean, why the prediction becomes so important. We'll see this one, that maybe the decision of a company, or a decision process, which clearly depends on the prediction. We'll see this one, that this is definitely one of the important thing that, well, we have the data up to a certain point, what is going to happen in future. I think the second one is also becoming exceedingly important about these compression purposes. Again, we'll give the example of this one, but let me just tell you. I mean, one of the very simple one. So suppose, I mean, it happens actually in general model. It is nothing to do with the periodic one, but in particular periodic case, it has been used. We'll say this one. That suppose you're looking at the ECG data, we'll see that it's a purely periodic in nature. Okay, we'll see this one. That for a normal person, it's a periodic in nature. Now, what do you mean by the compression? Okay, what do you mean by the compression? What we'll see this one that suppose I have a data which may be say 1 minute long or 1.5 minute long. You will see this one that because it is calculating in all this, or rather it is stored in every microsecond. So you'll see this one that a 1 minute data can be a significantly large one. Okay, but now if you have a good model, actually we do not have to keep all those data points. We can have only those parameters of the model, and that's it. And because if we have those, if we know the parameters of the model, that means I know that exactly I will be able to recover the original signal. Okay, so that is basically the whole compression is. Okay, the whole compression is basically that. By the way, I don't know how many of you are aware of this one. Around 15 years back, there is one nice musical device came out, that MP3. Okay, and actually they have used this compression technique there enormously. Okay, and which they have used actually this periodic data. They have used this one, and they have used this compression technique. And in fact, I don't know how many of you have seen this one during that time. They used to call this one that the compression ratio is 1:18. So basically that they could compress the whole data into 1/18th space. Okay, so it's a huge thing actually. Okay, so yeah, it becomes a very important one. So it is needed. Yeah, as I said. So let's look at a couple of data which are the periodic in nature, and this is one of the famous data actually, which is the airline passenger data, which is I think by the US Air, if I remember it correctly. It's a US Air, and they have this data. I think it is 1, 2, 3, 4, 5, 6, 7, 8 years data they have, and you can see that it is a clearly the periodic in nature, and actually this peaks at the summer. Okay, so the summer, of course, the traffic increases. So these are the number of traffics. That's what it is. I think in 1,000. Okay, that's what it is. So this number of traffics clearly is a maximum during the summer time, and then it drops. Okay, that's what it is. In this particular case, you can see that how important is the prediction. Okay, so clearly for any airlines company, particularly for this particular airline company, for them definitely the prediction is an important aspect, because they are trying to predict what is going to happen maybe next 2 years or next 3 years, things like that. So if they have this periodic data, clearly they want to have a prediction one, which is an important one. This is another very important data, which is basically called the brightness of the variable star data. And actually this brightness, which indicates that how far the star is from Earth. That's what it is. Okay, so you can see this one that it basically comes back. So this is the one which is the closest. Okay, which is the closest to Earth and things like that. Okay? That's the way it varies. Okay, here also you can see this one that, so we have this data. Okay, so I think this is in month. Okay, so you can have this data for this one, and then you want to predict it, how it is going to happen next. Okay, so these are the one. So the prediction here are important one. Same thing. This one has been this particular data has been collected in this IIT Kanpur signal processing lab, which is the particular vowel sound, this oo sound, which comes out to be. You can see this one that this is also clearly the periodic in nature. Yes, this is the one which is the ECG data for a normal person. Okay, so you can see this one that, well, we can have this ECG data, which basically gives you clearly a periodic pattern. And definitely, as I was mentioning, in this particular case, the compression plays an important role. The reason is very simple. Again, I don't know how many of you are aware. If you look at some of these Scandinavian countries, they actually collect ECG data for each child as soon as they're born, okay? And they keep this data for every month, okay? So after, I think, 5 years or after 10 years, I think they collect it every 6 months, and after that, they collect it every 1 year. So you can see this one, that the huge amount of data, they have to keep it just for one person, okay? So definitely the compression plays an important role there, okay? So definitely, which is important, okay? Yeah, so this is the periodic data in the 2 dimension. As I said, you can see that there is a symmetric in pattern, okay? This is a textured data, original textured data, which is a symmetric in nature in the 2 dimensions. Just looking at it itself, it is possible to say there is some kind of the periodicity, some kind of a symmetric nature in the data itself. Same thing, if you look at this, the 3-dimensional one, 3-dimensional basically means that we have the color. We have the color one, and the same thing. We have this colored, and that is also clearly periodic in nature because it's a kind of a symmetric one. Same thing, we have another one, which is a colored one, which is a symmetric in nature. Okay, so now let's come back to that, the basic formulations. Okay, so yeah, we go back to our class 9. Okay, when you are first introduced about this trigonometry, sine and cosine functions. Okay, the simplest periodic function is a sinusoidal function, and it can be written in this form clearly. So yt, which is a cosine omega t plus b sine omega t, and you can see this one that the period is 2 pi by omega. So it repeats in 2 pi by omega. Okay, so if you varies your t, it will come back again and again the same form, the same value of this yt every 2 pi by omega. Okay, so that's what it is. Okay, so that's a very, very basic one, basic periodic functions that we have learned in our high school, or rather in our elementary school. We are going one step further. Okay, now suppose we have a smooth periodic function. Okay, now suppose I go back. I have a function which is a smooth periodic function and which is mean adjusted. So we do not bother about the mean. So I assume this one that the yt has mean 0. Okay, so basically this yt, if you look at the sum of the yt's, which is 0, that's what it is. Okay, so mean adjusted with period 2 pi by omega, which can be written in this form. It's coming from this Fourier analysis, actually, nothing more than that, which is a very, very famous one. So I have any periodic function, I should be able to write it in this form. Okay, so that's what it is, and which comes from the Fourier expansion of yt. So basically, if you have your yt and you know that it's a periodic function, I know how to recover these ak's and the omegas. Okay, which is very simple, and that's what it is. Okay, so that's the way I can recover my ak's. So which is this way. This is the way I should be able to recover. Okay? That's a famous one. So this is basically the building block of this whole, the model 1, what I'm talking about. So this is already there. So as a statisticians, we know this one that, well, we'll never observe the data as it is. It will be always come up with an error. So instead of observing only these yt's, we'll be observing this quantity plus some error. Of course, there are some assumptions on the xt's. I'm not bothering about that at this moment. What is important here, that which is the noise component, and only thing I'm putting it here, that expected value of the noise component is 0. Okay, so that's the one what we are going to observe. Okay, so this is the model which first came into picture, but the problem occurs because of this k is equal to 1 up to infinity. You can see this one, that I have infinitely many parameters which we do not like it that much. Okay, so we modify this model. And the modification comes, which is we truncate it up to a value p, can be a large enough value p, but what is important here, I change my omegas. I do not keep the omegas to be fixed. Okay, so I am making it more flexible. So I am putting this one as omega k, unlike the previous one where your omegas were fixed and it simply comes out to be as omega k, omega times k. But here I am putting it as omega k. So I have p different omegas That's what we have, and I have my yt. So this is the model. So this is one of the most fundamental model in the statistical signal processing to analyze the periodic data. Okay, so we take it up from here. That's the way it has been developed. So I have this model yt, which is this one. So now you can see it's a purely statistical problem. I mean, what we have, you have this data, which is your yt's, and then now based on the data, what are the unknown quantities? Well, I have the unknown quantities p, of course. I do not know p. I have the unknown quantities a1, a2, ap. I have the unknown quantities b1, b2, bp, and I have the unknown quantities omega 1, omega 2, omega p. So that's it. So that's the basic formulation of the model, and based on the data, I have to analyze, I have to estimate those unknown parameters. That's it. Okay, so as you can see, the model clearly has two components. One is the deterministic part, clearly, which is the first one, which is clearly a deterministic part, and another is the random component. That's what it is. And if you look at it here, yes, exactly. That's what I mentioned already here, that well, our main problem is that I am trying to extract the mean vector, which is my mu t, which is the deterministic component, which is this quantity, okay, in presence of the error component xt from the yt. Okay? So from the data yt, so I have the data yt, which is at the point t1, at the point 1 to up to n. So that's the data I have, y1, y2, yn, and I'm trying to estimate the mean component mu t, which basically means all these parameters. That's what it is. Yeah, I just put it in this form. Okay, so this deterministic component p, a1, a2, ap, b1, b2, bp, omega 1, omega 2, omega e. That's what I have to find out. I have to estimate those quantities, and I need to estimate the error component also. Okay, and we'll see the reason behind it. Okay, so it is not this one that I can completely forget about the error component. I mean, which is not. Okay, which is not. I mean, and that's what we'll be doing it this one. So what is the procedure? What is the general procedure? I have this model. I put this model. I have this data, and then I'm trying to get whatever I'm trying to mention. Okay. First thing first. What we do? We make certain structure on xt. That's the first thing what we do. We make certain assumptions on xt, just like the linear model. I mean, we make certain assumptions on the error. Okay. So here also we make certain assumptions on the error structure xt. Okay. So now based on the error structure, we find out the deterministic component mu t. How do we do it? We'll come back to this one. But that is a general procedure what we are going to follow. I mean, make some assumption on xt, then follow some procedure, statistical procedure, and then get the component, estimate the component mu t, which basically means estimate those parameters, estimate the error xt. That is important. Okay, so you have this mu t, you estimate the error xt because you have the yt, the original data. What is important here? Verify the assumption. Okay, so whatever assumption you had make it in the first case, check this one whether it is satisfying or not. Okay, if it is satisfies, it's fine. All these things are absolutely fine. You can go ahead and do further analysis, whatever you want. But if it is not, then of course you have to go back here and you have to change your error structure. Okay, as simple as that. Okay, well, I mean, it's much easier said than done. Of course, I mean that plays a crucial role. So the way we do, I think that's the way I think the statisticians would like to do, that we put a fairly general structure on xt, which we believe captures a variety of error structure. Okay, and that's what we'll be putting it also. We'll see this one that. Okay, so that's what it is. So we put a fairly large structure, try to come up with some estimation procedure, and then when you try to verify this, it usually satisfies. Okay, it usually satisfies because we had put it a very, very general structure. Okay, we'll see what kind of things we do. Okay, so let's look at different estimation procedures. Okay, first I'll give you some of the, I would say, unorthodox estimation procedure, and we'll see some of the standard orthodox estimation procedure also. Well, as I said, that we'd like to put a fairly general structure on the error. And that's what we did it here. You can see this one that we did not put IID and things like that. We did not do that one. We put a structure, what is called a linear process. So that's the structure what we had put, xt, which is in this form, n et minus n, where these et's are IID, and only thing what I need, these ans are absolutely summable. Well, you can see that this is fairly general one. Actually, all your stationary processes, if you look at it, your ARMA process, AR process, MA process, all the stationary processes are part of these things. By properly choosing your AN, you'll come back to those things. So you have a nice, fairly general structure, and at the end of the day, what we'll see that this is analytically tractable, which is important. Okay, so that we'll see. So that I think makes it more interesting. Okay. As I said, first we look at some of the unorthodox method of estimations, and again, which actually was proposed mainly by those engineers, and of course it becomes extremely popular, and it has its own reason also. Okay, and we'll see. And the idea is what they're looking at. They're looking at this particular function I theta, which can be written in this form, which is yt cosine theta t squared, 1 by n whole square of this one, whole square of this one, which is approximately equal to this. Okay? Why they have taken this particular type of function? This is called a periodogram function. Why they have taken this one? Let's look at this picture. I think from the picture, if you look at it, it should be very, very clear. I have drawn this particular yt, where your yt, which is in this form, I've just taken p is equal to 2. Okay, I've taken p is equal to 2. My a is 3. My b is also 3, because 3 times cosine 0.2 pi t plus 3 times sine 0.2 pi t. Similarly, 3 times cosine 0.5 pi t and sine 0.5 pi t. Okay, so you can see that my p is equal to 2. My a, b, both of them are equal to 3. Rather, a1, b1, both of them are equal to 3. a2, b2, they're also both of them are equal to 3. My omega 1 is 0.2 pi, and my omega 2 is 0.5 pi. That's what it is. Okay? What I'm looking at it, I'm looking at this particular function, I theta. So my yt, which has been generated from there, generated from this particular model, and xt's, I'm just taking it to be IID at this moment. It doesn't really matter though, but I'm just, what is important here, the variance. Okay? So I'm taking here normal 0, and the variance 0.5. Yes?
This values of the parameters, that you have taken arbitrary, or is a specific reason for that?
We'll see this one, that why I have taken this one. Okay. We'll see this. The picture will tell you. Yes. So the reason actually I have taken this particular value, actually this is still not clear, it will be clear in the next one. Okay, because I'll be taking another set of values, and you will see this one, that what is going to happen. That's it. You can see that. It clearly shows there is because the omega 1, which is 0.25 pi, which is here actually, omega 2, which is 0.5 pi, which is over here, and you can see that it shows clearly there are 2 peaks. Okay, because my p is equal to 2, and clearly it shows that. So that means if we have this particular model, if I don't tell you what is my p, if you simply plot this one, you can get some idea that, well, my p is 2, and my omega 1 and omega 2, which is over here and over here. So that's the reason that it becomes so popular. But let's see what is the problem. I think then you will see this one, that what is the problem. I am taking a slightly different set of values, okay? Which is, the first one I'm keeping it same. Okay, I'm keeping it same, the first one, which is 3 cosine 0.2 pi, and the sine 0.2 pi, which is the 3. What I have changed the second one. Instead of 3, I have taken 0.25. Okay, I have taken 0.25, and which is over here. And here, you can see this one, this also I have changed. I have made this variance larger. Okay, I make this variance larger because previously it was 0.5. Now if I plot this function I theta, the same function I theta, what you will see, you'll be just able to see just one peak. Okay, so you cannot see the second one. So the natural question is why it happens. Well, the reason is very simple. What it is called in the standard one, it all depends on your value of a1 squared plus b1 squared, a2 squared plus b2 squared, and sigma squared. That means if this a1 square plus b1 square divided by sigma square is large enough, then the peaks you'll be able to see. But if the a1 square plus b1 square by sigma square is not large enough, you won't be able to see the peak. And that's what is going to happen, because you can see that in this case, your 0.25 square plus 0.25 square. This one is also, I am making it larger. And that's the reason that you are not able to see the second peak. Whereas in the previous case, I do not have that, because this one is 3 square plus 3 square. And I have this one is smaller. So that is basically the main reason. What they called in the signal processing literature, they call basically the signal to noise ratio, which is nothing but in this particular case is a1 square plus b1 square divided by sigma square. Nothing more than that. Okay? So that means, although the method becomes very, very popular one, but it has its own drawback. Okay? So let's look at what the statisticians would prefer. The statisticians, of course, they have their own nice way to look at the things, and we are looking at these least square estimators, which I think is a very, very robust one. We know this one that well. It works well for many of the nonlinear regression problem and things like that. So we're simply trying to look at this quantity, yt minus this quantity square of that, and I'm trying to minimize all these with respect to these unknown parameters, which is ak's, omega k's, bk's. And sometimes maybe I have to do with respect to p, but that's a different thing. Okay, so I'll keep my p constant at this moment. I'll come back to this one, that how to estimate, because we have lots of this procedure which is already there for the model selection one, which can be done. So, but what is important here that, well, let's keep p fixed. I'm trying to estimate this ak's, bk's, and the omega k's, which is simply by this least square method. Okay, what are the numerical issues we face? Okay, and so that actually becomes very much a challenging problem. Okay, it's a highly nonlinear problem. Okay, it's a highly nonlinear problem, and the main problem is the least square surface has several local minima. Okay, what it means? It simply means that, well, if you plot the least square surface, I mean, it's highly nonlinear as it says, and it has a lots of this local minima, which basically means that really doesn't matter what kind of numerical procedure you use, unless you have an extremely good initial guesses, you'll be always get stuck into the local minima rather than the global one. Okay, so because you are trying to find out the global one, you are trying to minimize that quantity, what we had mentioned this one, the least squares. Okay, the residuals. Okay, I'm trying to minimize the residuals, but it's very difficult to get it unless you have an extremely good initial guesses. Most of the standard algorithm, like the Newton-Raphson algorithm, actually does not converge. Okay, that's what it's well known. It's well known this one that if you look at the standard Newton-Raphson algorithm or the Gauss-Newton algorithm, the standard one is not converging. And the third one, I think, which is more upsetting, even if they converge, often it converges to the local one rather than the global one. So you really do not know. You might get a solution, but that is not a solution at all. I mean, what you are looking for is just some value. That's it. So basically, it is not a solution. But another one, which is also, I think it is extremely important, that if your P is large, it becomes a very, very higher dimensional optimization problem. I mean, see, because we will see this one, that one of our example, we have seen this one in the case of this ECG data, your P can be in the tune of 50. Okay, so you can see this one, that how many parameters you have. Okay, so basically you have a parameter 50 omegas, you have 50 A's, you have 50 B's. So basically you have 150 parameters. Okay, and estimating those 150 parameters is not a very easy job. Okay, so that's what it happens, that if P is large, it becomes a higher dimensional optimization problem, and you need extremely accurate, as I said, extremely accurate initial guesses. And you can see this one, that if you have to choose initial guesses of those higher dimensions, forget it. You're not going to get it. Okay? So, we'll come back to the numerical issues. But let's look at the theoretical issues, which was not addressed actually by the engineers, and which, if you look at this model, which is typical nonlinear regression model, we can put it in this way: yt is equal to ft theta plus xt. This ft theta, which is whatever I have. So this ft, which is a deterministic component, and you have a very, 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 very standard very, very general result by this Jenrich and Wu, and what they have shown that, well, under certain conditions on the FTs, they have proved the consistent the asymptotic normality. But what is happening in this particular case that, well, they do not satisfy those conditions. Okay, they do not satisfy those conditions, the sufficient condition. Actually, the conditions, all these conditions are sufficient conditions. Okay, so they did not satisfy the sufficient condition of this Wu and Jenrich. So the general results cannot be used. The general result cannot be used. So you have to do it separately for this one, and which is. And once you do these things, it becomes clear why their results do not work, because it has a very, very different convergence rate. Okay, very, very different convergence rate of the parameters. Actually, for the linear parameters, the convergence rate are the usual one, n to the power minus half, which what we usually see in all the linear regressions, in most of the nonlinear regressions. If you look at it, we have the convergence rate, this one. But what is surprising, that if you look at the nonlinear parameters, it has a convergence rate which is much faster, which is n to the power minus 3 by 2. Okay? So it has a both positive and negative point. Positive point, that means it is possible to get very, very accurate estimates. That's what it says, because the variance is of the order of 1 by n cube. Okay? So that means you can get a you can obtain, it is possible to obtain a very, very accurate estimates. But then you need a very, very efficient algorithm to get that one. Okay, because most of the times you know that you are not achieving what you are supposed to get it. Okay, which is not true in case of the linear model. Okay, so that's what it is. Well, the sequential procedure has kind of solved that one. Two aspects it has solved. First of all, it has solved the problem of finding out the estimators, particularly for large P, and it can solve finding out the initial guesses also in a great extent. Okay, and the nice part about that one, anyway, let me just mention. We'll see this one that it is much easier to implement compared to the usual least square estimators. Okay, and which is like this: you have this YT, and you know that there are P components. I'm assuming P to be known. Doesn't matter at this moment. I'm assuming P to be known. You know, what you do, you just try to find out the first component. Okay, this A, B, and omega by doing only one, not all of them at the same time. You do one at a time. Okay, that's what you do. And once you get this A, B, and omega, then you take it out the effect of that from the data. That means what you do, you form a new data set y tilde t, which is yt minus a hat cosine omega hat t minus b hat sine omega hat t. That's what you do, and you repeat the procedure p times. Okay, so you can see this one that it saves extremely about the computational issues. Okay, not only that, we'll talk about even the initial guesses also, because see, you can easily see that. Say yt is equal to a cosine omega t plus minus b sine omega t. Actually, this particular problem, although I have 3 parameters, but it is a one-dimensional optimization problem. Okay, because I can always write a in terms of omega and b in terms of omega. Okay, I should be always able to write it. The least square solutions of the a and b for a fixed omega, I should be able to write it. Okay, so finally, actually, the minimizations of this one, which can be obtained just by minimizing in a one-dimensional optimization problem. So that means, see, and solving a one-dimensional optimization problem is simple. Okay, and not only that, getting the initial guesses is also not very difficult, because what we can do, because we know that your omega is lying between 0 to 2 pi, and then you can easily get it. Okay, so that actually solves these computational issues tremendously. So the natural question is, what is going to happen about the theoretical properties? Okay, but which somehow turns out to be quite advantageous. Okay, let me just put it here, how much progress it can make. You can see that if you simply look at 25, p is equal to 25, I need to solve a 25-dimensional optimization problem. Okay, but if you look at the sequential one, you have to solve basically 25 one-dimensional problem, which is clearly much easier to do it. But what is important here? Well, I think let me just mention it here. What is important here that, well, what can be proved, that the least square estimators and the sequential estimators, they have the same asymptotic properties. I think that is the nice part. So you're not losing any efficiency. You're not losing any efficiency as far as the estimation, as far as the estimators are concerned, but you can gain tremendously about the computational issues. Next one, which is a very, very counterintuitive estimator, and which actually, when you have first got this one, that we are kind of, it was difficult to accept it. And the reason is that, well, I'm not going into the details, but I'm just giving the final form. As I said, that if you look at, again, P is equal to 1, just a one-dimensional, just a one-component model, if you look at the simple Newton raption, okay, it's a very simple. It looks like this, where this Q prime and the Q double prime is nothing but the first derivative of the residuals, and this is the second derivative. So since it's a one-dimensional one, so this is just a one element, this is also another element. Both are functions of omega. So this is the iterations you need to follow. Okay, so you start from any process, iterative process, you start with an initial guess, you go to the move to the next one, simply by these things. Okay? And it is known this Newton-Raphson method does not work. It usually diverges or it converges to the local minimum. Well, we had to make some kind of what they call the step factor modifications. This 1/4. Well, this 1/4 is not arbitrary. It came from a purely theoretical reasons with some expansions and all these things, and that's what we can modify the usual Newton-Raphson procedure with this kind of a modification. And once we make this kind of a modification, what is the most important thing is that, interesting thing is that, actually, you can produce a better estimator than the least square estimator. In the sense, the variance of this estimator turns out to be smaller than the variance of the least square estimators. Although the order is same, n to the power minus 3/2, but the value of the variance in this particular case is smaller. Okay, so that's kind of interesting. Okay, so so these are the main theoretical results. The least square estimators are consistent under mild assumptions on the errors. Least square estimators have the convergence rate n to the power minus 3/2, as I mentioned. Sequential estimator also have the same rate of convergence as the least square estimators. Asymptotic variance of the super efficient estimator, which I had mentioned in the last one, which is smaller than the least square estimators, just what I mentioned. And the periodogram estimators are consistent, but it has the convergence rate, which is much smaller, or rather much larger, n to the power minus half. Okay, so definitely they are not efficient. Okay, but which has become a very, very popular one, as I said, because it has been used for quite some time. Okay, so this is more or less about the background of the first model, which has been the main motivation about the second one, which is there. So I'm coming to the second one, and this particular model becomes quite popular in the signal processing literature, and that is called the chart model. I'll come back and give some applications of this one, but I just put it in simply the mathematical form, because I do not want to go to the explicit derivations, but the mathematical form, which can be written in this way. And as you can see this one, that this is the extra term, what is there, compared to the previous one. This is the extra term what we have, this is the extra term what we have, and of course that xt, which are as usual, as before. Well, this is the most general one, because instead of one, I have a p of those. Okay, that's what I have. So I have p components chart model. Okay, and well, one of the thing, the reason that it has been seen this one, that well, you can see this one, that basically, if you do not have this component, if you have only the alpha t's, what they call this one, the frequency, so these alphas and the betas are called the frequencies, okay? So these alphas and the betas are alpha, in this particular case, alpha, that is a frequency. So frequency is constant. But if you look at this one, actually the frequency is changing, okay? So because that's what it is. So say you can put it in this one, actually, alpha t plus beta, okay? Whole thing times t, okay? So that's all other way, okay? So your frequencies are changing, okay? So that is the reason this one that this becomes a important one. But some of the applications, what they have found it quite extensively is that in that many audio signals, the signals of that's the reason that the name chirp came, and some of the things what they have prove this one in the radar and the sonar systems, apparently this particular model has been used quite extensively, okay, where basically the frequencies are changing. And even this EEG data also, what it has been shown that the chart models can be used quite effectively. Okay, again, as I said, I'm not going into the any of those heuristic estimation procedure because there are quite a few. But I'll be sticking to those which has a solid theoretical backing. Okay, so that's what we'll be mainly talking about, and about their implementation also. Well, so basically I'll be sticking to the least squares and the approximate least squares. Satyaka, I'm sorry, because Satyaka has a work on this one. He has done on this Bayesian one, and I did not put it here. I'm sorry for this one, but he has done. So anybody can ask him. He has done recent work on the Bayesian one on this particular one. But I'll be mainly sticking to the on the classical one. Okay. But in our review paper, we are putting your work, of course. Yes. Yeah. So So this standard one. I mean, we don't have to think much. We can at least formulate the problem very easily, and that's what it is. Okay, actually these are not approximate, these are least squares. These are not approximate, these are least square estimator, I'm sorry. So these are least square estimators can be obtained by minimizing this residual sums of squares. So these are least square estimator. Okay, so that's what the standard one. The standard one, what it is. Okay, so we go ahead and do this one, but well, I did not do in the last case, but in this particular case, as I mentioned, that well, if you look at this, Q of A, B, alpha, beta, as I said, this capital A and B, these are the linear parameters, and these are the nonlinear parameters. So what we do, for a fixed alpha, beta, I'll try to find out the solutions of this A and B, which minimizes this quantity, and then I'll minimize with respect to alpha, beta, the standard procedure. And actually, it can be shown, they give the global optimum also. So that's what I do. I put it A hat alpha, beta, B hat alpha, beta, and these things are very simple because these are the linear models, so which is nothing but your X transpose X inverse X transpose Y, where the matrix X, which is nothing but this cosine and sine, your alpha beta term, just a column vector like this, which is 2 by P. That's it. Okay, so you can easily get this A hat and B hat in terms of alpha beta. So what is finally boils down that well, this quantity is just a function of alpha beta. Okay, so I have a two-dimensional problem now. I need to minimize this quantity in the 2 dimensions. Okay, that's what it is. But what is the numerical problem? Again, here the problem is much more compared to the usual least square case. Okay, here problem is much more because here the surface is much more nonlinear. Okay, because of the presence of this alpha beta with this n squared, it's a much more nonlinear one. And because of that, it's really a computationally challenging problem. Okay? So it's a really computationally challenging problem. And in fact, to start the initial guess, one needs a 1 by n cross 1 by n squared grid search for that. So you can easily imagine, suppose your n is simply 100, so you can go up to 10 to the power 4, 10 to the power 5. So just to get the initial guess, you need to search this many points, okay, grid points. Okay, so it is not a very easy problem as far as the computation is concerned. Well, let's look at alternate one, again, which is similar to the periodogram one, and so it is. We call this one as a periodogram type estimator. Some people has given us a different name also, chirpulate and things like that, but the same thing. So we're just talking about the same thing. At I of alpha beta, I have say yt cosine of alpha t plus beta t squared 1 by n, and I have the same thing over here. Okay, it is exactly the same thing like the periodogram one. What we have in the periodogram one, there I did not have this quantity. I did not have this quantity. Okay, it was exactly the same as before, and I have this I of alpha beta. So what we want to do, and in fact, actually here also, if you plot it in the 2 dimensions, it can be shown that it has those 2 peaks at the point alpha beta in the 2 dimensions. Okay, so that's the whole idea about this one. You try to maximize this I of alpha beta with respect to alpha beta. Okay, that's what we do. Let's look at some of the theoretical considerations. First of all, least square estimators are consistent. Again, we have to go back to this standard nonlinear regression problem. What we know that this particular model also is not going to satisfy those conditions of the generic channel. Okay, it's not going to satisfy. So we have to develop these things in a completely afresh. Okay, so we have to do it from the very beginning itself. Again, we cannot use the result even for the case what we have done it for the sinusoidal model, so we have to do it. You have to develop it separately. Okay, so the least square estimators are consistent under finiteness of the fourth order moment. So this is one of the extra conditions what we need. We still could not get rid of that. I mean, we need these finite fourth order conditions on the error random variables, and then it is possible to obtain the consistency of this one. What is important? Amplitudes, which is same as the sinusoidal model, they have the same convergence rate, which is n to the power minus half, which is a very, very standard one for any nonlinear regression model. So this is not very surprising for the linear component, which is n to the power minus half. What happened even in the linear models also. But if you look at the frequencies, which is n to the power minus 3 by 2, which you have observed before, that means the variance of the least square estimators of alpha will be 1 by n cube, of the order of 1 by n cube. But what is important here, that if you look at your chart component, the beta, which is alpha t plus beta t square, if you look at beta, which is n to the power minus 5 by 2. So that means it is possible to get much more accurate estimates. Okay? And that makes it more difficult also because of this convergence rate n to the power minus 3 by 2. Okay? But again, at the end of the day, what it is, that the least square estimators are asymptotically equivalent to the approximate least square estimator. So that can be established, that well, they are asymptotically equivalent, so it really does not matter whether you work with the least square or whether you are working with the approximate least square. Both of them will give you the equivalent estimators. But well, let me tell you one thing, but numerically, both of them are equally challenging. I mean, one is not better than the other. Both of them have to solve the same kind of problem. Okay, so there is no escape on that. But what is problem here? Yeah, so that I already mentioned. Okay, so the problem comes after this. Okay, so now what we are trying to do, we have just done so far only for one. Okay, we have done these results only for one, but how to extend this one for the p? Okay, so the natural question is that, well, we try to do the sequential method, but actually we could not get that one, that they are going to give the equivalent results with the least square estimator and the sequential least square estimators. We did not get it for quite some time because the results what we need in case of the sinusoidal model, the first model, those results are very standard. Okay, so using those standard results, we could show this one that the sequential estimators and the least square estimators are equivalent, but similar thing is not true in this particular case. Okay, and so the natural question is, will the sequential method work in this particular case? Okay, what we are seeing it at the beginning that, well, numerically it is working fine, things are going okay, but we could not do this one sequentially. And finally, we came up with it's a completely obscured place. It's a number theoretic result. Okay, apparently it's a purely number theoretic results. What it tells, because it's a book in number theory actually. That's what we got, and that too also not a very, very nice form it was there. But finally, what you could get it from there, that, well, if your theta 1, theta 2 lying between here, which is in our case, then except for the countable number of points, I am going to get these three results. Okay, so these are the three results which looks fine. I mean, which looks actually all right, but the proof of this one is not very easy. For example, if you drop out this theta 2, the proof is very simple. That's what we had in the case of the sinusoidal model. If you drop out this theta 2, the proof is very simple. Okay, if you drop out this theta 2, the proofs are very simple. Okay? But when you have this theta 2, things are completely different way. You have to use this algebraic number theory method, and then you have to get this one. So, but fortunately, using these three results, we can prove that the sequential estimators will give a equivalent one for the usual least square estimator. So they are equivalent in that sense because we had these three results. The next thing comes, what about the asymptotic distributions? What about the asymptotic distribution of the sequential estimators, and what about the asymptotic distributions of the least square estimators? Are they equivalent? Well, again, we are struggling for quite a bit, and what we obtained, actually we could not get the result. What we got a number theoretic conjecture actually. Okay, what we got a number theoretic conjecture, which is this one, and which is there pending for almost like more than 50 years. Okay, the conjecture says that, well, actually this thing is going to happen. Okay, and we need this result. We need this result, and using this one. So if you believe in the conjecture, okay, so again we were trying to. I mean, once you see this conjecture, I mean, we saw that there is no point in trying to prove this one, because I think several people have tried, all these number theorists have tried, but at least we are trying to see this one, that whether this is true numerically. Actually, that we have seen even before also, before coming to this one, we have seen these things before also, but which is verified actually. And using this number theoretic conjecture, actually, I should not say result, is a number theoretic conjecture, it can be shown that the least square estimator and the asymptotic least square estimators, their asymptotic distributions are also same. Okay, so that I think makes the thing complete, provided the conjecture is correct. Okay, so that's what we have. Based on the above conjecture, it can be shown that the sequential estimators and the least square estimators they are equivalent. Okay. Okay. Well, the natural thing comes that, well, I mean, if you move away from the least square estimators. Okay, so the natural thing is that the simplest one, instead of going for the usual M estimator, first let's look at what is going to happen to the least absolute deviation estimator. Okay, and well, it can be shown that, well, the proofs are completely different now, but it can be shown that they are consistent. Okay, so they are consistent estimator, and well, they are asymptotically normal, but the distributions are different. Distributions are different, but they have the same rate. Okay? They have the same rate. But here we have another problem. Here, the problem here is that, well, it's a much more numerically challenging problem, because in the case of the least square, I can reduce the problem from the 3 dimensions to 1 dimension, but here I cannot. So I have to do the things simultaneously, and of course, we have some method. We know that the linear programming problem can be used to solve the least absolute deviation estimator, but well, I mean, it is not a very we have not yet implemented it using the LPP, but we have just did it the brute force way, and we just got the theoretical result mainly. Okay, so that's what it is. So, but I think that can be it can be done actually as a problem. That, well, how to implement this one, the linear programming problem, to get this estimator. Okay, and well, in this particular case, we really do not know how to extend the result for p greater than 1. Okay, we have the result only for p is equal to 1. We have no idea how to extend this one for p greater than 1. Okay, so this is another, it's a kind of a different type of algorithm, and which is, I just briefly mentioned, I'm not going into the detail. It is what they call this the finite step efficient algorithm. So what it tells this one, that we know in a finite number of steps, it reaches the order of accuracy what we are looking for. Okay, and in fact, this particular method shows this one, that in the 4 steps you can obtain this one, and this is the procedure. You start with an estimator of this order. You start with an estimator of this order, and then you have a certain method to go to the next step, and you got this one. Okay, so I'm just not going to go to the detail. Okay, so now let me just come to this 2-dimensional model, which also becoming an important one in the signal processing, and we'll see this one, that some of the applications, particularly we'll see this particular model, it's a two-dimensional model, as you can see. The data is in M and N. Okay? The data is in M and N, which is in this form. And interestingly, actually, this particular model, which has been used in fingerprinting. Okay? So the fingerprinting data, which has been used to model with this kind of model, two-dimensional chart model, and some of its generalizations. Okay, so that's what it is. Well, the problem remains the same. I have a general model also for k is equal to 1 up to p, because the previous one is just one component. I have a p component, and the problem remains the same based on the data, the two-dimensional data. We have a reasonable error assumptions. We have a two-dimensional error assumptions. Based on the data, I want to estimate all these parameters. Same problem. There is no difference. Yeah, as I said, these are the two places where it has been used quite significantly. One is the texture imaging. The two-dimensional model have been used, and this fingerprinting, that also it has been used quite extensively. Again, there are mainly two methods which have a theoretical backing, and at the end I'll mention one of those. Another one, which is more numerically efficient one, but they have the same kind of a convergence rate. I'll mention at the end of those two, of the other one. Okay, these two are the standard one. The same way as we did in the one dimensions, we just go to the two dimensions, trying to minimize that. We have to develop the theoretical properties from the very scratch. We do not have anything. We cannot use any other previous results. But what we have, if you look at the alpha 1 parameter, which is of the order of n to the power minus 1, m to the power minus 3. If you look at alpha 2, which is n to the power minus 1, n to the power minus 3. If you look at beta 1, which is n to the power minus 1, m to the power minus 5, and the beta 2, which is m to the power minus 1, n to the power minus 5. So you can see that as the dimensions are increasing, actually you are getting a better and better. It is possible to get better and better estimators. That's what it is. And at the same time, it is becoming more difficult to get those things because of the higher dimensions. Okay, that's typical curse of dimensionality. And in fact, it can be shown theoretically along the same way that if you increase one more, you have basically three quantities here, so you'll be coming one after another. Okay, so that's what it is. Again, computational issues is a tremendous problem about the computation one, because the same thing, you can see this one that I needed this kind of a grid search to get this one, and therefore even n is equal to 100, I need 10 to the power 6, because I have a 2 here, 4, 5, 6, so 10 to the power 6 grid search. It's a really a tough one to handle. So this is the one what we had mentioned that which can be done actually, which is we had implemented this one, and this is basically trying to reduce the two-dimensional problem to one-dimensional problem. Okay, that's what it is. So what we do, we put it in this. Just for the just for this ease of this presentations, or the ease for the understanding, I just write this thing in the two-dimensional matrix form. Okay, so this is my y11, y12, y1n, and so this is basically the second one is varying, this one is my first one is varying. Okay, so now what I'm going to do, keep it in mind that I need this kind of a grid search to get the estimates of the two dimensions. So I'm trying to avoid that. Okay, so what we do, we look at each of the rows separately. Okay, so if you look at this, particularly this row, and if you go back to the basic model, and if you keep the first one fixed, if you keep your, say, m is equal to m naught, and if you look at this one as y m naught n, small n is varying from 1 up to capital N, you can write this model actually a one-dimensional. Okay? It's a very simple. Actually, you can go back to, let's look at this one. It is much easier to see this one, that if you keep your m fixed, okay, so this thing becomes a completely constant one. So now you can write this y m naught n for small n is equal to 1 up to capital N, it's a one-dimensional chart model. Only thing what is going to happen, your linear parameters are different, okay? But the frequency and the frequency rate, they will be all same for each row. So that is an important thing, okay? So for each row, if you go back to this two-dimensional model, if you go back to this two-dimensional data in this one, so if you look at the first one, okay? So this particular one, I should be able to write it as a one-dimensional chart model where the frequency and frequency rate, they are all same for each row. What is different are the linear parameters. But that does not really matter. I mean, because what I will do, I can look at the least square estimator now because I will be replacing the linear parameters anyway for a given nonlinear parameter. So even if the linear parameters are different, I should be able to weight it properly and take the sum of all these things to take care about finding out the nonlinear parameters. Okay, so I can easily obtain alpha and beta from the rows, and exactly the same thing I can do it from the columns. Okay, from the same thing of the columns also, I can see this one, I can find out my gamma and delta. And once I get this alpha, beta, gamma, delta, I can easily get the linear parameters. That's not a problem at all because by simply using the linear regression technique. Okay, so that's what the method says. So that means basically we are reducing the two-dimensional problem to a one-dimensional problem. Again, the question arises: what about the properties? What about the efficiency of this one? Is that the same as the least square estimators, or it is different? Fortunately, what happens this one that well, what we could do that under the assumptions of the IID errors, it is not the general that linear process errors. If you have a IID errors, what we could show that the estimate, their orders of convergence are same. Okay, so basically the properties of the least square estimators and the properties of these, what we call this one, the efficient estimators, they have the same properties. Okay, so that asymptotic properties, let's say. Okay, that's what it is. That's what it is. So that actually gives you a really computational facility to implement this one. Okay, so so we treat each row as a one-dimensional model. We treat each column as a one-dimensional model. The asymptotic variances are same with the least square estimators or the approximate least square estimator because they are basically the same thing. Okay, so this is more or less about the two-dimensional model and the one-dimensional model, what we are talking about. And now I'll be talking about some of the related models which can be thought of. I mean, which definitely of things can be done quite a bit. One thing is, of course, if you look at the three-dimensional model, which basically means that it is not only the two. I have third parameter, third dimension also, where the third dimension can be the color. Okay, so whatever we have mentioned so far, it's a black and white, but we can go to the third dimension also, where the color is the third component. Okay, so that is another one. This is becoming an extremely popular one, what is called the polynomial phase. And let's go back. What is the polynomial phase basically means that if you look at the one-dimensional model, one-dimensional chart model, let's go back to the one-dimensional chart model. Yes. Yeah. So if you look at this one-dimensional chart model, what you can see this one, that this is a quadratic one. So it is alpha t plus beta t square. But you can have actually polynomial. Okay, so it is not only alpha t plus beta t square. So you can have alpha 1t plus beta 1t square up to p, okay, or q. Okay, so you have a polynomial there. So you can have a model there, and people are using this one quite extensively, which is a polynomial chart model. That's what the polynomial phase model, not the polynomial chart one. When it is 2, then it's called a chart. Otherwise, it's called a polynomial phase model. Okay. Another one, I think what I had mentioned about the random amplitude chart model, which is also becoming extremely important because, again, I mean, lots of these real life data which can be analyzed using this random amplitude. So basically, if you go back to the chart model, you have this A cosine alpha t plus beta t square plus B sine alpha t plus beta t square, where your A and B are fixed. Okay, but there is no need to keep this A and B fixed. Actually, you can take it to be random. Okay, you can take it to be random, and that's what they call this one as a random amplitude chart model, and then try to try to develop the methods. Okay. This one actually becoming just came out, I think 3 years back. Again, see, this model actually come up from these different engineering applications, and this particular model, what they have done it. So then in this particular case, what they have done that, if you go back to the chart model again, let's go back to the chart model. So p-dimensional chart model. Okay, let's go back to that. Yeah, so let's go back to this p-dimensional chart model, which is YT, which is this one. And this fundamental chart model, what they say that, well, they're saying this one that, well, my alpha k, actually all the alpha k's are not different. Okay, alpha k can be written in the form of k times alpha. That means the frequencies are a constant multiple, what they call as a fundamental frequency. Similarly, your beta k, the frequency rate, is also a constant multiple of a fundamental frequency rate. Okay, so basically the model becomes a simpler model. Okay, but the analysis becomes difficult. Okay, so basically your ak cosine, instead of alpha sub k, it is k times alpha t plus p sub k, not that it's k times beta t square. So basically you have only 2 parameters. Okay, only 2 parameters, alpha and beta. Rest of the frequencies or the frequency rate are constant multiple of that. Okay, so that becomes a very, very important one, and so we call this one, they call this one as a fundamental frequency chart model. That's what we have, and then finally, what we have this chart-like model. That is also a model what we have proposed recently, which is that, well, I'm not looking at the model in the form of cosine of alpha t plus beta t square. I just break it up. I look at it this one as a times cosine alpha t plus b times cosine beta t square. Okay, so I just break it up into 2 components, and what we have seen that actually it behaves exactly like the chart model. Okay, so it is almost impossible to make a distinction between the two, but analytically it becomes much more easier to handle. Computationally also it is much more easier to handle. So that, I think, will make it more useful in that respect. Okay, I think with this one I'm going to just stop it. I just mentioned about the collaborators with whom. So this is Professor Bai. I mean, I call him as my friend, philosopher, and guide. I mean, he was there, and so he is basically a theoretical statistician. So we had quite a bit of work with him. It is his son actually who is an electrical engineer. So we have done some work with him also, and the rest of them are the PhD students. So all the work are basically with these people. That's what we have. And so these are the references that I mentioned. These are mainly the references what in the statistical literature what we have. So this is the first one, I think, what we had published about the CHARP one, where we had proved these asymptotic properties of the least square estimators. And then we had gone for this is for the IID errors. This has gone for the stationary error. Interesting part is that the methods are completely different. Okay, so it is not that. This is the one where the super efficient one, where we had proposed that if you modify the Newton-Raphson algorithm, you can get a better estimator than the least square estimators. That's what it is. This one we had proposed a efficient algorithm for estimating the one-dimensional chart one, this one for the two-dimensional one, and this one for the least absolute deviation estimator what we have. And this is the one for the multiple chart one, where we had used the results of the number theoretic results what we need. This one, and this one actually a recent one what we had put a very, very general model for a general polynomial phase model. This one is the one which had gone for these approximate least square estimators. That's what we have with the recent one. And this is the one what we had given for the two-dimensional approximate least square estimators. Well, this is the recent paper what we have done it for the modified Newton-Raphson algorithm for the fundamental frequency type model. And so this is a very, very famous book. I mean, please have a look at this. I mean, this is a very nice book. It has dealt with these sinusoidal frequencies mainly. Okay, and yeah, this is one of our book what we had done. Okay, I think with this I'll just stop it. Although it is not 2 hours, but I think I'll stop it. Yeah, any questions?
Any question?